All right, so we're in section 7.3. Thank you. So we're going to talk about something called partial fraction decomposition. It sounds complicated, but the process is very straightforward. All right, so far what we've done in math, or for the types of problems that we've wanted to solve in math, we have something like 1 over x minus 1 plus 2 over x plus 3. And in order to do what we needed to do, or solve the problems that we need, the types of problems that we need to solve, we had to add these fractions together. And to add these fractions together, what do we do? Got to find a common denominator. So we end up multiplying this by x plus 3 over x plus 3, and the other one by the other fraction by x minus 1 over x minus 1. We multiply these together. We combine the like terms in the numerator. When we do that, we get a 3x plus 1. And then I'm going to rewrite the denominator, multiply this all out. We FOIL this, and we end up with x squared plus 2x minus 3. So far, that's when we solve problems. Usually we want to do that. Well, what we want to do today is we go the other direction. We want to start with 3x plus 1 over x squared plus 2x minus 3. And we're going to do this process. A wiggly line means process, that we call partial fractions. So we're going to do this process, and we're going to go the other direction and get to 1 over x minus 1 plus 2 over x plus 3. So we want to go the other direction. So, and because in the future there will be problems that are impossible to do when the fraction is written this way, but very easy to do when the fractions are written this way. What we call each of these, each is a partial fraction. Because it is a part, each one is a part of the fraction that makes up that whole rational expression. These two things together is called the partial fraction decomposition. So 1 over x minus 1 plus 2 over x plus 3 is the partial fraction decomposition of that expression. So that's our terminology. And we call the process partial fractions or partial fraction decomposition. So partial fractions undoes finding a common denominator. So what I want to do is describe the process kind of in words. The verbal description makes it sound kind of esoteric, but it's really pretty straightforward. So I'm going to do the verbal description, then we're going to go through some examples of what that verbal description is telling us, and then we'll do some examples of the entire decomposition. Yes. Unusual. Strange a little bit.
That's a big word to use. I don't know big words.
All right. So let me write. So we're going to write. I'm going to write the process. And I'm writing all the pieces of the process for completion. Some of them we won't really need to worry about, but I want to write them out just so we will see them. I'm going to reconnect to some of these things. We'll reconnect with them in chapter 2, which is what we cover next. So we have some function f of x equals n of x over d of x. N for numerator, d for denominator. And each of these are polynomials. So some kind of x squared plus 2x plus 5, something like that. The first thing that we need to think about, and this is a part that we won't have to worry that much about it, but we'll reconnect with this in chapter 2, is if n of x over d of x is improper. And what we mean by an improper fraction with polynomials is the degree of n of x is higher. That's what an improper fraction means. So, for example, if n of x was x to the 5th plus 3x cubed something, 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 and the denominator was 2x squared plus 3x plus 5. If that is the case, we use long division. And this is a part we'll reconnect with in chapter 2. Use long division and then do partial fractions on the remainder over d of x. So we won't have to worry about it. If you go on and take Calc 2, not AP Calc BC, but if you take Calc 2 in college, you will do this. If you take Calc 2 with me, then we do some of this. Second, this is where we usually start. Factor the denominator. And when we factor a polynomial, we're always going to be able to factor it into linear terms, something like x plus 5, or quadratic terms, x squared plus x plus 1, that won't factor anymore. That's when we factor completely, we end up with either linear factors or quadratic factors. For each linear factor, I'm going to say px plus q, and that linear factor possibly could be raised to some power. So it could be x plus 3 squared. So x plus 3 times x plus 3. We could get that in our denominator. For each of these linear factors, we include the partial fraction now, what we're going to do is include a partial fraction for each possible power of this thing up to m. So I'm going to say a1 over px plus q. A1 is just a number. Plus a2 over px plus q squared. So, for example, if we had with numbers, if we had a common denominator, our common denominator was 25, we could have a 5 here, and we could have a 25 there that combine to give us a common denominator of 25. And we're going to keep going. A3 is just a number. Px plus q to the third, and we keep going until we get to our exponent of m. So we include every possible power of px plus q. And then our goal is going to be then to figure out what a1, a2, a3, dot, dot, dot have to be in order for this to work out. For each quadratic factor, I'm going to write that as ax squared plus bx plus c. And that possibly could be raised to some exponent. We factor it, and this we can't factor this anymore. We include the partial fraction I'm going to say fractions because we have more than one. And I'm going to write this one, since we used a's here, we need a linear factor, b1x plus c1, over the first power of that quadratic. Plus, and then we need to include all the possible powers of this quadratic factor, b2x plus c, but we have a linear factor in the numerator. So this is going to be squared, and then we keep going, plus, and this is 2, and then we get bnx plus cn. We keep going until we get up to our exponent n. So we're accounting for all the possible denominators that give us our common denominator of ax squared plus bx plus c to some power. All right, so there's the verbal description. Sounds kind of intimidating, but it's really not. So what I want to do is go through several examples of how we write these out, and then we'll go through the process of finding these a's, b's, and c's for our partial fractions. All right, questions so far? And then when we actually do the whole process, we'll see why we're talking about this in the unit about systems of equations. So for example, and what we're talking about here is the form of the decomposition. So some of your homework problems will say, find the form of the partial fraction decomposition, and that's what this is talking about. So I'm going to start with 3x plus 5. We'll keep essentially the same fraction each time, just change the denominators a little bit. So we factored our denominator, and we get this. 3x plus 5 over x times x plus 1 times x minus 2. We're going to say this equals, we need one partial fraction for the x. We need another partial fraction for the x plus 1. And we need a third partial fraction for the x minus 2. Each of these is a linear factor. So we have 3 partial fractions, one for each factor. And then eventually what we're going to need to do is figure out what a, b, and c have to equal. All right, if we had 3x plus 5 over x squared times x plus 1, I can think of this as 3x plus 5, x times x plus 1. I need to include one partial fraction for the x. I need to include one partial fraction for the x times the x. So this is to the second power, so I need to include a partial fraction for this all the way up to whatever power this is. And we need to include a partial fraction for the x plus 1. So since this is x squared, we need to include an x and and an x squared. If this were 3x plus 5 over x squared times x plus 1 squared times x minus 2. So we factor this. This would be a pretty messy one to factor, but we say we factored it, and this is what we get. We're going to include a partial fraction for the x plus a partial fraction for the x squared. We're going to include a partial fraction for the x plus 1. We're going to include a partial fraction for the x plus 1 squared. And we're going to include a partial fraction for the x minus 2. This one would be a very messy problem. We don't have to do any that are that complicated. So questions on this, finding the form of the decomposition so far? All right, let's take a look at one where we have a quadratic factor in the denominator. So we factor the denominator, and this is what we get. X squared plus x plus 1 won't factor anymore, right? Can we all agree on that? So we can't do any more factoring, so we have to include a partial fraction for the x. But since this one is quadratic, we need a linear numerator, bx plus c, and we're including a partial fraction for the x squared plus x plus 1. And we have, let's do one more, and then we'll go through the process. So we factor the denominator, and we end up with an x squared plus x plus 1 squared. We are going to need to include a partial fraction for the x, one with a linear numerator for the x squared plus x plus 1 denominator, plus a linear numerator and a quadratic denominator for the squared part. This one potentially would be kind of a messy problem, because then we have to figure out what A, B, C, D, and E are. So this is what we call finding the form of the decomposition. And our job then is figure out what the A's, the B's, and the C's are. All right, so questions on that part. So this process is what we verbally described on the previous page, except for the part about doing long division. We're not going to worry about that now. All right, so let's go through this process and figure out why we're talking about this in the systems of equations unit. So let's do the problem that we started with.
Would you like a reading of these poster? Sure.
So let's do the decomposition. 3x plus 1 over x squared plus 2x minus 3. And I already told you that this factors as x minus 1, x plus 3. That's our first step. And then we write the form of the decomposition. We need, these are both linear, so we need a partial fraction for the x minus 1 and a partial fraction for the x plus 3. So what I'm going to do is write this here, and I'm going to write the steps that we take next to it. All right, so our first step is to clear the fractions. So I clear the fractions by multiplying everything by this common denominator. So I'm going to multiply by x minus 1 times x plus 3. Multiply this by x minus 1 times x plus 3. And multiply this by x minus 1 times x plus 3. So I'm multiplying everything by this common denominator. Well, these are going to cancel. This cancels here. This cancels with this. And this cancels with this. So I get that on the left, 3x plus 1 equals a times x plus 3 plus b times x minus 1. So that's what I get after I clear the fractions. Second step, distribute. So on the right, I'm going to distribute. So I get 3x plus 1 equals ax plus 3a plus bx minus b. Now, when you start doing this more, you won't do this. You'll kind of start combining steps, but I want to make everything explicit. Now I'm going to collect like terms. So I'm going to say 3x plus 1 equals ax plus bx plus 3a minus b. So all the things with x's together, all the things with no variables together. If I had x squareds, I'd have all the things with x squareds together. Same with x thirds. Now I'm going to factor. That should be a b. Yes, I forgot my. We're going to factor the right-hand side. So I get 3x plus 1. I'm going to factor the x out, but I'm going to write it like this. A plus b times x. And plus these are just numbers, 3a minus b. And now we're going to equate coefficients. So what we mean here is whatever's in front of the x on the right, this has to be true. This equation has to be true no matter what. Whatever is in front of the x on the right has to be the same as what's in front of the x on the left. So a plus b has to equal 3. Whatever doesn't have any variable on the right has to be the same as whatever doesn't have a variable on the left. So 3a minus b has to be 1. And now what do we have? System of equations. So we've that little system of equations. If you had an a, b, c, and d, you'd have 4 equations and 4 variables. All right, so what's going to be an easy way to solve this system? We could do substitution. How about just add them together? Add these two together. 4a equals 4. So a equals 1 and b equals 2. And we figured out that 3x plus 1 over x squared plus 2x minus 3 equals 1 over x minus 1 plus 2 over x minus 3. And this would be the partial fraction decomposition, just like we said right at the beginning. Yeah?
What would be the point of putting it into partial fraction?
So the point is in the future, when you do a process in calculus called integration, you cannot do it on this thing. You can do it on this easily.
So it's for like future stuff that we're
Yes.
doing?
And so now in my Calc 3 class, when we see problems that have to do with partial fractions, the students right away, they know, oh, that's partial fractions. So what partial fractions is going to be a piece of a larger problem. Here it's the problem in and of itself. In the future, partial fractions is a piece of a bigger problem. All right, let's look at another one. Let's look at one with repeated factors. So this one is already given to you in factored form. We don't have to factor the denominator. They did it for us. So we're going to write out the form. We need 1 for the x plus 1, and we need 1 for the x plus 1 squared. Now we're going to clear fractions. So I'm going to multiply by x plus 1, multiply everything by x plus 1 squared. I'm not going to write out all the steps here. And I'm going to write this as 2x plus 4 equals one of these x plus 1s cancels with one of these. So I get a times x plus 1 plus b. Now I'm going to distribute. And I'm going to equate coefficients. Whatever's in front of the x has to be in front of the x on that side. So a has to be 2. And a plus b, whatever is by itself, without any variables, has to be the same as that. So b is 2. That one's an easy one. So we get that 2x plus 4 over x plus 1 squared equals 2 over x plus 1 plus 2 over x plus 1 squared. All right, questions there? Okay. What if there were an x squared on this side, but not on this side? What if this had a cx squared on this side? So what would c have to be? 0. If there's no x squared, that means that the coefficient in front of it is a 0. Yeah, Megan.
On like a test or quiz, when we have a problem like this, do you want us to show all the steps that can be combined?
If you did this, that would be fine.
Okay.
Yeah.
So with the C, if we had a C on the left side as well as the right, the same rule applies?
This A's, B's, and C's only ever appear on the right. So this is always the numerator of your fraction.
So if in every situation where there's a C on the right, there would always be 0.
Not necessarily. If there, so whatever's in front of the x squared on this side has to be equal to what's in front of the x squared on the other side, no matter what it is.
Oh, I see what you're saying. It's just two variables.
Right, right, right.
So it would be Y.
Right, right. All right, let's look at another one. This one with a quadratic factor. All right, so what's our first step here? Factor the denominator. Wait, how are we going to factor it? We have a common factor of x. Six. All right, can we factor x squared plus 4x plus 6? The only factors of 6 are 6 and 1 and 2 and 3. And we can't combine those to get a 4, right? Nope, so if we can't factor it, we just leave it like this. And we're going to include a partial fraction for the x. And then since this is a quadratic, we have a linear numerator.
Yeah, what's that number on the top right? Is that an L?
What number is that on the top right?
C. Bx plus c. And now what's our next step?
Multiply by the common denominator.
Clear the fractions. So I'm going to multiply everything by x times x squared plus 4x plus 6. And you don't always have to write this out. I'm just showing it just so we see it. All right, so these all cancel. Hello? These cancel, so I get x plus 6. When you clear your fractions, you should always just get the numerator on the left-hand side. And this is going to be a times x squared plus 4x plus 6 plus bx plus c times x. Now I'm going to distribute, and I'm going to distribute and collect my like terms together in one step. So I get an a x squared, and here I get a b x squared. Here I get a plus 4ax, and here I get a plus cx, and here I get a plus 6a. So we get a plus b x squared plus 4a plus c x plus 6a. So this tells me a plus b has to equal, there's no x squared over here, so a plus b has to be 0. 4a plus c, whoops, has to be 1. And 6a has to equal 6. I wanted a different color. There we go. 6a has to equal 6. So a equals 1. From the first equation, that tells us b equals -1. And 4a plus c has to be 1. So c is -3. And so I get that x plus 6 over x cubed plus 4x squared plus 6x equals 1 over x plus -x minus 3 over x squared plus 4x plus 6. All right, questions there? Not quite. I want to show you a shortcut. This method will always work. The shortcut doesn't always work because it doesn't help all the time. Let's say we've got our problem. We get our problem down to So it looks like this. 6x minus 3 over x squared plus 3x minus 4. So what's our first step here? We got a factor. So how's this going to factor? X plus 4, x minus 1. I'm going to include a partial fraction for the x plus 4 and include a partial fraction for the x minus 1. I'm going to clear my fractions. So I know when I clear my fractions, I'm going to multiply by x plus 4 to x minus 1. And here I get an a times x minus 1 plus b times x minus 4. Because I'm multiplying everything by x plus 4, x minus 1.
So you plus x plus 4.
Yes. Thank you. All right. So here's the shortcut. This has to be true no matter what. This equation has to work no matter what x is. So what would be a convenient value of x to plug in there to make our lives easier?
1 or negative 4.
Let's plug in if x equals 1. This whole term goes away. And I get 4b. 6 minus 3 is 3. Sorry, 5b. 5b equals 3. I plug in x equals 1. This goes away. 6 times 1 minus 3 is 3. 1 plus 4 is 5 times b. So b equals 3/5. And what's the other convenient value? If x equals negative 4, we plug in negative 4. So we get negative 24 minus 3. Negative 27 equals negative 4 minus 1. Negative 5a. This one goes away. And a equals 27/5.
Why will that not work for every
So, what's that? Yeah, so this one would be kind of messy to solve otherwise, and I'm just going to leave it. We could write it out here. So let me go back here. For this one, what would be a convenient value of x to put in there?
0?
X equals 0 would be good because that goes away, and that would give you 6a equals 6, so a equals 1, but that's the only convenient value. So from there, you would have to do the rest of it to get this. So sometimes it'll save a little bit of work, but then you still have to do a system. But with linear factors, it's really nice with linear factors because here, what's a convenient value of x to plug in? Negative 1. So you plug in x equals negative 1, but then you still have to figure out the a plus b part. So it can be helpful, but sometimes it doesn't give you all of your coefficients. All right, questions? Okay. All right, so the first three here are just looking for the form of the decomposition. And for these four, you're doing the whole process.